Hello and welcome to yet another video in this series of solving ordinary differential equations of higher order. In this video, we are going to learn about differential operators. Differential operators play an important role in solving if d of y is equal to r. So d is the differential operator that we are going to see in a while. Fd is the symbolic form of all the differential operators taken together, right? So in the previous video we have solved Fd is equal to 0 as our auxiliary equation. The Fd here is same as that. If you want a little revision, you can go to a previous video and have a watch at it. All right. So we have it. We'll first define what the inverse operator is, and then we'll use our inverse operator to find out the particular integral, or at least get to know about how to find out the particular integral, the theory behind it in this video. Let us say that capital D is d by dx, which means this is the first order differentiation with respect to x. Now, when this operator d is applied on a function y, we shall get dy by dx. So let d be the operator. And for a function r containing only x, so this looks quite familiar, right? So this function r can be thought of the right hand side of a non-homogeneous linear differential equation with constant coefficients, as we have seen in the exactly previous video on this playlist. So for a function containing only x, we shall define the inverse operator of d on r by 1 by d of r is equal to integration of r with respect to x, right? So let's take an example and see how this works. So let's take an example of r to be x to the power n, and this satisfies the condition that r contains only x. This, by the definition that we have looked at little while back, over here is going to be x to the power n integrated with respect to x. And this, my friends, is x to the power n plus 1 divided by n plus 1. This is pretty simple, correct? Now, here, this is a improper integral, and there should be a constant. So we have just considered c to be equal to 0 for the simplicity of our calculations. We could take any value of c theoretically, but for the simplicity, for brevity of the solution, we have considered c to be equal to 0 as we are going to look at our particular integral. So, given a non-homogeneous linear differential equation with constant coefficients whose general term is given here, we shall write down the symbolic form. Right? We have seen this before. Again, dn, capital Dn, is the nth order differential operator with respect to the independent variable, which is x here, plus k1 times n minus 1th derivative of y plus k2 times n minus 2th derivative of y with respect to x, and so on, all the way up to kn times y. That's the left hand side, and the right hand side is r. R is a function of x only, and this can be written as fd multiplied by y. Well, so this is not really a multiplication, this is fd of y, which is equal to r. So our differential equation, our non-homogeneous differential equation, which has quite a dangerous look over here, can be written as fdy is equal to r. Now what we need to find out is a particular solution y, right, given that we have got r and fd. So the method to do that is basically find out r divided by the entire left side of the auxiliary equation using the symbolic representation, right? So the pi, the particular integral, is going to be r divided by fd, and that's how we find out the particular integral. In the next videos, we will try to understand how each of the r has its own form of particular integral. So, for example, if r is a polynomial, or if r is an exponential, or if r is a trigonometric function, how can we actually identify the particular integral for each of those? Well, it's a vast topic. In this playlist, t- we shall restrict ourselves just to a few of them. So, to watch more, please subscribe to the channel, and we'll see later. We'll see you soon, right? Bye.